This is a video to present LE-GEOM, as in lesion geometry, which is a a prototype software that is capable of extracting glioblastoma diameters, measurements, directly from a pre-existing segmentations. These are all the details for this invention. The premise is that in this era, AI-based segmentations of brain tumors are becoming widely available. But RANO-compliant linear diameters still require humans to draw the diameters, essentially. So the relevance of automating the diameter extractions from segmentations is that we could remove the need for human intervention if we streamlined AI segmentations to automatic diameter extraction. That would be less time consuming, doesn't need training humans to do it, and prevents any possible operator dependency of this task. One objection could be, why not use volumes and disregard diameters entirely? I would be on board in general with this solution because RANO 2.0 allows the use of tumor segmentations for tracking volumes over time. However, linear diameters still have value, and the most important aspect is that you need to identify measurable disease with linear diameters. These are the guidelines for the RANO 2.0 implementations. And as we can see, the volumetric segmentation should be used only after we make sure that there is measurable enhancement as per RANO 2.0 with diameters. Whereas if there's no measurable disease as per RANO 2.0, we shouldn't use the segmentations at all, and we should abstract the volume to zero. So there's definitely a role for diameters. And beyond the measurable disease aspect, measuring the maximal cross-sectional diameters is still important because it gives complementary information and helps the comparability with historical data. LE-GEOM is it outputs RANO-compliant diameters, and the most important aspect of this is that it handles correctly the shape irregularities, such as resection cavities, holes, or digitations of the lesion. And it's not simply maximal Euclidean distances of the edges of the segmentation. This is the reason why you don't want to go that way. The problem is that the Euclidean distances of the segmentation translate into non-RANO compliant diameters because they will end up crossing the resection cavity, crossing non-tumoral tissue and or ventricles and whatnot. So that's not the way to go. Instead, we figured out a way to use a set of engineered instructions explicit in the code, and the software follows all of the instructions. So it's not AI, it's not a trained software that learned by itself. It follows explicit instructions. It is deterministic, so it's fully reproducible. If you run it multiple times on the same case, you will always have the same result. And another feature is that it's adjustable. There's a couple of adjustments that can be done to customize it. One central aspect is that it can be set to be more or less tolerant to irregularities, holes, and whatnot, and we're going to see an example in a moment. And then it can also be adjusted for faster versus more thorough, let's say. And the other aspect is that it outputs plots and images for quality control. So you want to see what diameters it came up with. So now we're going to see three different examples that are going to highlight different aspects of this software. So the first example is a case with measurable disease around the surgical cavity, which is a classic RANO problem to identify that measurable disease around the enhancing pericavitary tissue. The following case is the opposite. So there is a cavity, there is enhancing disease around it, but no measurable enhancing disease. And finally, there is another case with more abundant enhancing disease, and we're going to see how the tolerance setting can change the output. So for now, there is no user interface, so I'm just going to run the code from a terminal window. All you need is one image, so for instance, a post-contrast T1 and a segmentation. I'm going to show how this case looks like. So there is enhancement surrounding the surgical cavity. So as a radiologist, I would like to measure the nodules that are around it without being confounded by all of these additional enhancement that is more linear shaped. Just for context, let's see what the segmentation looks like This is the segmentation that was done by AI. So again, no humans did anything for this at the moment. So let's run the code, and I'm going to show how it works. So when you launch the code, it's going to tell you what it's doing. So the step one is to search for the presence or absence of measurable disease. It does some iterations, and it's already done. The first thing that it does is that it outputs a plot that gives you an idea in 3 dimensions of what it found. The gray dots are all the segmentation points, segmentation voxels. You can see there's a kind of a hole in the middle, whereas the actual enhancing tissue is more the part that is more like that is thicker at the edge. And it did find it puts a ball to show where the measurable tumor is, 1 by 1 by 1 centimeters, and it identifies where it is. It prints out found measurable disease, and it shows it in green, meaning that it did find measurable disease. It will also output an actual image that we're going to see in a moment. But for now, let's run the second step. The second step is try to find the maximal in-plane diameters, and it already ran, and it found these diameters in one of the regions, and it's showing us where it found them. And the diameters are 30 by 24 millimeters. And we also want to see the output. There are 2 outputs. One output is measurable disease, whether there is measurable disease that, as we saw, was identified, and it's placing a little ball to show us where it is, a 1 by 1 by 1 measurable disease according to RANO. Measurable disease is important because if we use segmentation volumes, we're only allowed to track the volumes if there is measurable disease. And the other aspect is that only patients with measurable disease can be enrolled in recurrent clinical trials. And the other output shows us where it found the maximal diameters, which in this case is right here. And as you can see, it did respect the hole. It didn't cross diameters through the holes or through the cavity. It just found this superior nodule here that, as a radiologist, this is the one that I would probably isolate for diameters too. Now let's see a different case where there is no measurable disease. It's a similar case to the other one with a cavity and enhancement of the region around the cavity, but in this case, there is no RANO measurable disease. There is no areas where I can track diameters that are 1 by 1 by 1 in the 3 dimensions. So I'm just gonna redirect where this other case is and relaunch the algorithm as it is. So step one, searching for measurable disease, and it's thinking, it's doing some iterations. And it output this diagram. The ball is blue. You remember that the ball was green when it found measurable disease. It's blue when it doesn't, and it outputs no measurable disease. We're also going to see the images in a minute. And now it is converging to the maximal diameters, and it found diameters towards the bottom of the lesion. In addition to these plots, we want to see what the imaging outputs are. So the first one is called, in this case, no measurable disease. And it put a ball at the bottom of it to show where it tried to find measurable disease. As you see, the output ball is blue, whereas it was green when it did find measurable disease. And now let's see the other output, which is the maximal diameters. It did find maximal diameters, and it's outputting 37 by 24. But of course, it only found these diameters at the bottom of the enhancing rim. So it's just because that simple slice cross-sectionally isolated a region that had large diameters, but of course, like the 2 pieces of information should be read together. There is no measurable disease, so we don't care really about the diameters. We don't care really about the segmentation volume. Let's see a final case. This case is a case with a lot of enhancing tumor. So here, the challenge is a bit different. Of course, there is measurable disease, but the challenge is we want diameters to isolate something that we can call RANO compliant. So, and I'm gonna show what is the difference if we change the tolerance level. So first of all, we redirect where the data is, and we rerun the code as is at the moment. Again, step one, it's searching for measurable disease. Maybe I'm not gonna open the images for measurable disease this time because it's obvious there's going to be. So it did find measurable disease, and this is the plot of where it find it. So it gives you an idea of what part of the lesion was identified, but it really doesn't matter. There may be measurable disease in other spots too. That's just a way to confirm that there is. And now the most interesting part for this test is looking at where it converges for diameters. So this is our output for now, where it converged to two cross-sectional diameters towards the bottom of the segmentation. It also prints out a vertical diameter, but that's not the main aspect, let's say, of the software, also because it doesn't matter for RANO, as long as you have measurable disease, of course. Let's take a look at the output segmentation. The output segmentation looks like this. So it converged to these diameters that isolate a big region of tumor. It didn't go to regions where where the diameters would cross the segmentation, the cavity, the surgical cavity, nor the ventricles or anything like that. It isolated a region that that has contrast enhancing disease continuatively. It was a little bit tolerant that there is a little bit of irregularity of the lesion. As a radiologist, I would probably isolate something like this to measure this lesion. Let's see. I'm just going to quickly change the tolerance parameter. So make it a little bit less tolerant, so stricter. And let's rerun the code just to show what the differences are. The measurable disease part is going to come out exactly the same. The two tasks are fully independent, whether there is measurable disease and what are the diameters. So the tolerance or other customizable aspects can be customized independently for the measurable disease task versus the maximal diameters task. They're independent and they're independently customizable. So in this case, I only changed the features for the maximal diameters. I made it a little stricter, and as you can see, converged to smaller diameters, and I'm going to show why in a second. The diameters that it picked are these ones, so it kind of isolated this lesion rather than the whole thing. And the reason is that I set it to be less tolerant of these irregular shapes. So it didn't like how irregular it was. So it converged to these diameters, which are smaller and more conservative. Of course, if we change the tolerance parameter or other parameters, it's going to converge to different diameters. So it's not going to be consistent with itself if we change the settings. But the important part is that it will be consistent with itself with the same settings. So for a clinical trial, maybe you can do a test run on a couple of cases, decide what level of tolerance in general you like, and then you can just analyze all the cases with the same parameters. Maybe will not always converge to diameters that are the same that a radiologist would do, but it will be consistent with itself across all the cases. And I would also argue that not all radiologists would also converge to the same diameters that another radiologist would draw.